Great.
Okay.
So, yeah, apologies for that late start. We were having a few technical difficulties getting going, but finally here. So my name is Michael Jack. I'm the director of the Otago Energy Research Centre, and this is part of our seminar series. So we've got, it's my great pleasure to welcome Dr. Alan Jones as our speaker here today. So he's a senior scientist with 19 years of experience in research on climate change and carbon dynamic impacts to a range of forested systems around the world. He joined Scion 5 years ago from the UK, and his work has focused on addressing climate change related forest challenges in New Zealand. And he's going to talk about this work today. So over to you, Alan. I'll just minimize some of these things so we have a little bit more.
Thank you. Okay, so I'm going to run through quite a lot in this presentation, but start off with quite a bold statement, which is the title of my presentation, which is Short Rotation Forestry Holds the Key to Lowering Fossil Fuel Dependency. I'm hoping by the end of this presentation I've convinced you at least part of the way that that statement is correct in a New Zealand context. So, slide movement. Keep the mouse. Okay, so just click the left.
That should be.
Okay, cool, right. Okay, so where do we start with our work at Scion on this? Well, there's a whole range of factors, but one of those is some very strong signals that indicate there will be increasing bioenergy demand over the next decade, developing through government signals suggesting this way. The New Zealand Climate Change Commission report in 2022 showed a number of scenarios. Some of those scenarios indicated a strong component of bioenergy making those net zero targets for the future, and also this combined with a phase out of coal use by the mid 2030s, which is coming online. Against this context, there is a reduction in wood supply capacity taking place by the mid 2030s, as you can see on this graph here. The blue stuff is what's actually been harvested, and everything in the green there is your forecast harvest moving into the future. So it's kind of a perfect storm: increasing demand, reduction in supply, particularly from our forests to supply that bioenergy. So that was why we addressed this idea of short rotation forestry, and how could that maybe fill in that gap and make that work. So just to give you an idea of what that demand for bioenergy looks like on a national scale, so this is a heat map that was put together by MB, showing the range of high demand coal and liquid fuels for industrial process heat nationally. So you can see a number of these areas. These are all coal and gas industrial heat burners and boilers, things like lime kilns, milk processing factories, things like that, but also energy, electricity production as well. It uses huge amounts of coal and gas, which is all going to be under threat over the next 10 years or so. So we're going to find another way of plugging that gap, and bioenergy is one potential part of that will enable that to take place. So where we started with our work at Scion, in 2021 we held a workshop at Scion and thrashed out a whole load of ideas around short rotation forestry. And from our brainstorming session, we came up with a whole range of research questions, and here are some of the highlighted ones which I put here. So what dropped out of that was the idea of which regimes or species would work for short rotation bioenergy forestry. How do we minimize transport costs to future energy demand centers that I showed you in that previous slide? Where is the lowest cost land? How does the ETS or the emissions trading scheme have those carbon values interact with this? Can we use them? How does that work out economically? And finally, how do we also engage landowners and investors? So the kind of scope of our research over the last 3, moving on to 4 years now, is illustrated on this slide here. So we have, in 2021, we did an initial scoping study looking at the economics and just feasibility, testing the feasibility of how this might work. In 2022, we did a detailed spatial assessment of economic and growth performance from short rotation forestry. And in 2023-24, we did a whole range of assessments, including a climate mitigation effectiveness assessment, handbook that we launched for growers, investors, and government agencies. So first of all, you may be wondering, what is forest bioenergy? Well, just to clear that up, I'll put this slide in here. So forest bioenergy takes the form of anything you want to basically use fossil fuels for now. You could use forest wood products to supplement. So on the left-hand side, we've got wood pellets and torrefied briquettes. There's a solid biofuels taken straight from that forest biomass, directly turned into solid energy, which will supplant anywhere you're burning coal, essentially. And on the right-hand side, we've got examples of liquid biofuels. So you can convert that forest biomass or any biomass into a whole range of liquid biofuels, or actually any synthetic products you might want to make. Anything you can make currently from oil or coal today, you can actually convert into from forest biomass as well. So those are our main areas, and that's what we're hoping to achieve through this. So I mentioned this word short rotation forestry, and this is the subject of my talk, but what actually does that mean? Fundamentally, what we're talking about would be illustrated relatively well by the image shown on this slide here. So we're having trees planted at relatively high stocking densities, and we're choosing fast-growing species, and what that essentially means is growing trees at 650 to 1250 stems per hectare. And then in a New Zealand system, we're looking to harvest those between 12 and 18 years of age. So the candidate species, we went through a whole literature review process. We looked at the performance of a range of species, and we came up with a shortlist which was mainly focused on their growing performance and their adaptability to a range of different environmental criteria. And from that shortlist, we resolved that to 4 main candidate species. And they're roughly in the order of preference that I'll say them out now. So Pinus radiata is our top candidate. Eucalyptus fastigata is the next one down. Eucalyptus regnans is the one after that, and Eucalyptus nitens is the one after that in terms of preference and suitability. Now, Pinus radiata is an obvious candidate because it grows really well. It's got a fast growth rate, and it's very adaptable to a whole range of conditions nationally. So it's no surprise that that's there on that list. We also have the 3 eucalypt species there. Now, they have one advantage over Pinus radiata in that they grow quite rapidly in their initial growth phase. So they're suitable where you want to harvest rapidly, as opposed to Pinus radiata, which you can harvest. It does more growing later on in its growth phase. But put together, those 4 species allow you to adapt to a range of different environmental and growing criteria. So for the purposes of our analysis, we focused on establishing short rotation forestry on land use capability class 5 to 7 land. And this is typically sheep and beef grazing country, as you can see illustrated here. The reason for this is that we're trying to minimise land costs in our sort of model, our working hypothesis of how this would work. And so this area is low value hill country, and currently it's economically marginal for sheep and beef farming. So a lot of these landowners will be potentially looking to diversify into other forms of income, of which we suggest that bioenergy and forest bioenergy would be one potential candidate for future investment. So why are we focusing on those LUC class grazing lands, those high, that sort of steep hill country? Well, as I've said, this is low cost land, but on this diagram here it illustrates very clearly that what we're trying to do is avoid conflict with crop production. So if you look at the LUC 1, 2, 3, 4 areas, that's prime cropping land, and by putting bioenergy on the less economically productive land, we're avoiding that conflict between food production, which is what we want to avoid. So we conducted an analysis of potentially profitable areas using this sort of working model of short rotation forestry on the hill country, using those 4 species. And what we wanted to do was discover which areas nationally would be profitable and economically viable using the productivity of those species, the growing availability of those species. So this is why we conducted this analysis. So I'll just run through briefly the results that we found here. So I'm focusing on here, these are results for Pinus radiata. So this map you can see on the left-hand side shows a whole range of different colours, and I'll get on to what those mean in a moment. But essentially, all those coloured areas are potentially profitable for short rotation forestry nationally. So how that analysis was completed was to look at the biophysical capability of each of those species to grow, or in this case, Pinus radiata, and the potential for that species to grow and produce a sufficient yield. But it also interacts with, our analysis interacts with the value of the land, and also transport distances to nearest processing locations for those bioenergy products from those lands. So it's a kind of complex analysis, spatial analysis that integrates both biophysical growing performance of those trees overlaid with the cost of the land and the transport distances. So we're focusing again on, as I said, land use 5 to 7 land. We excluded red zoned land from our analysis as well, so that's that very high, steep hill country that is prone to erosion and other factors. We also excluded things like dock estate, existing forest, and so on and so forth. And then the different colours that you can see on this map here relate to the different income streams from the emissions trading scheme. So what we're doing with this is we're allowing within our analysis a return from the ETS at different values of carbon per tonne. So we start off at without carbon is the purple zones in there, and then we move down all the way up to $150 per tonne carbon there. Interestingly, with this analysis, even without any income from the ETS, we got 450,000 hectares nationally that was economically viable for afforestation, even without ETS income. So, but what we can basically say is the more ETS income you get, the more area you can viably afforest with short rotation forestry. So I mentioned that transport costs are a challenge, and what we're essentially trying to do, or what we're suggesting we might want to do with this, is plant in relatively remote locations that are areas of available cheap land, and that builds up a bit of a tension in terms of the transport costs, because a lot of our areas of high demand, our processing centres, are going to be away from those areas of production for the forest there. So ideally, we want our bioenergy productions located near those centres of high energy demand or processing capability in the future. However, what we might want to say is, as I say down here, decentralised processing could provide economic stimulus to more remote areas. So we can sort of flip this whole map on its head, as it were, and actually say we could actually start to build processing locations in remote areas, such as in the East Coast and places like that, where we would actually want to plant those forests and actually provide economic stimulus in those areas. So we acknowledge that this is a problem, but it's something that's not impossible to overcome in the future. So from this analysis, we identified, and what I've indicated here is 6 priority wood supply regions for short rotation bioenergy. So this is areas that we indicate that the economics and the land availability and the distance to processing locations in the future kind of all adds up quite nicely. So we've got Northland, Central North Island, the East Coast, Hawke's Bay, Canterbury, and Otago Southland, all areas where there's potential high demand for bioenergy in the future and capacity to actually grow those forests as well. So, for the purpose of this presentation, I was directed to a number of questions from your group, and I'm attempting to address some of those now in this next section of my talk. So I've titled this "Forest Bioenergy Concerns" or "Forest Bioenergy Questions," and I acknowledge that there are some challenges potentially and some risks with going down this route. So that's what I'm going to talk to now. So I just want to start off with a couple of basic kind of principles that I hope we can all agree on. So the most the statement I'd like to start off with is just to say that the most important climate change mitigation is to transform energy and transport systems to leave fossil fuel carbon in the ground. And I think we can all agree on that one. In New Zealand, 50% of our emissions come from transport, electricity generation, and industrial process heat, as you can see on this pie chart here. So everything on the right-hand side is agricultural or waste emissions, and the rest of it there is all of the processes that could potentially take bioenergy products. So each of those processes are possible to decarbonise through other sources of energy, but it will not necessarily be possible nor economically feasible to rapidly decarbonise all of those processes on the left-hand side of that pie chart there within the next 10, 20 years, which is what we need to do. So one of the key benefits of forest biology and bioenergy products from forests is that it can help reduce carbon emissions in those sorts of sectors that are challenging to decarbonise. So where we have electricity generation or industrial process heat, or marine transport or aviation fuels, we can use all those bioenergy products from forests to help abate the carbon emissions from each of those sectors. And it's one of the ways that uses is relative. We can do that immediately now quite easily with the existing technology and existing supply capacity of forest products from country nationally. So first question, so why is forest energy presented as a true alternative to clean hydroelectric, solar or wind energy? I guess I'd first like to sort of respond to that question and say, well, I'm not presenting bioenergy as an alternative. What I'm saying is with everything I'm presenting here, that this all works alongside all other forms of renewable or sustainable forms of energy. But it helps support and contribute to that. But one of the things about clean hydroelectric, solar or wind energy is that they all have emissions factors associated with them. So for every gigajoule of electric energy you produce, you have an emissions factor associated with this. For hydroelectric, these are some figures I pulled out here. I'm sure there's a range around these, but these are just the figures that immediately came to hand. 6.64 kilograms of CO2 per gigajoule produced. For solar, 7.26 kilograms CO2 per gigajoule produced. And for wind farms, 4.17 kilograms of CO2 equivalent per gigajoule of energy produced. If we move on to bioenergy from forests, I put this figure up here of negative figure, 0.1 kilograms of CO2 per gigajoule. Now, I will couch, there's an important caveat with that statement is there is a lot of variability around that factor. And that's why I put these green arrows on this slide here, is to illustrate that that figure can both go up, we can make it less negative or more positive in terms of the emissions from bioenergy. It can also go down, we can make it more negative. It depends on how effectively you manage the system, where that bioenergy comes from. So this is the kind of key thing about this is that forest bioenergy has the capacity to actually produce energy while also taking more carbon out of the atmosphere, but there are some risks around that, and I do acknowledge that. So also there was a question that I saw about the air pollution and risks associated with burning wood fuels, and surely we should be using fossil fuels instead. Well, coal is a really nasty, mucky fuel, and it produces far more air pollution than those solid fuels from forests. So that I think is how I would respond to that, is that instead of burning, we'd definitely be better off burning solid biofuels from forests rather than coal in terms of just air pollution itself. So yeah, or sulfur pollution and so on and so forth that you get from coal. So how is forest biomass any different to burning coal or other fossil fuels? So what we're suggesting and what like to think about in terms of biomass burning from forests is that the biomass carbon is carbon circulating in the system. It's not changing the total amount of carbon dioxide in the atmosphere. That's the ideal scenario here, that is we are just taking in the same amount, and as long as you maintain the size of that biomass pool in that forest, the whole system is neutral in terms of its carbon emissions. Now, if we sort of, think about what else is happening, well, the fossil fuel burning, fossil fuel carbon is a one-way street. So every time we're using fossil fuel carbon, we're increasing the total amount of carbon dioxide in the atmosphere. So what we want to do is use less of this and more of this and other renewable sources of energy to reduce the amount of oil burning and fossil fuel burning going into the atmosphere. So if we don't have those bioenergy factors or other renewables displacing emissions from oil, this is what we end up with, is more emissions going into the atmosphere, which is obviously what we want to avoid. So an ideal emissions diagram, you might say, an idealized system of an integrated renewable energy system would look something like this. So if we include bioenergy into this system, we can see on the right-hand side those renewable systems that I talked to earlier. They have small positive net emissions factors into the atmosphere, and in an ideal scenario, ideally set up, biomass from forests would be net neutral, or actually negative in terms of its emissions, which I'll move on to later. So that's the kind of ideal that we're looking for with bioenergy integrated in a renewable energy system. So does the net effect of a forest biomass and its net effect on emissions depend on land use that bioenergy forests are replacing? So another question that I was directed to here. The answer is yes, resounding yes, and that's what I'll sort of talk to you now. So if we plant a biomass forest, and in the process of developing and growing that biomass forest, we actually increase the amount of total forest biomass, we will be reducing the amount of carbon dioxide in the atmosphere. So what we end up with is a massive big arrow on the top there, taking in carbon out of the atmosphere into forest biomass, a smaller arrow along the bottom with that extraction back into the energy system, a smaller arrow going back into the atmosphere, and the net effect is a smaller CO2 pool in the atmosphere. That might seem a bit extraordinary. How could that work? Well, one example I can give you of this that works very appropriately here nationally is the idea of converting grazing land into a forest biomass system. So if we move from that emitting system, which is grazing land, emitting nitrous oxides and all sorts of things into the atmosphere, methane, if we convert that into a forest bioenergy system, we're actually reducing the amount of CO2 in the atmosphere and creating energy that we can use as well. But this can also work the other way. So if we somehow develop a forest bioenergy system and we do it really badly and design it terribly and don't take into account all the consequences that can take place, we can actually end up with decreasing the forest biomass carbon, which is definitely what we want to avoid. So that will increase the amount of carbon dioxide in the atmosphere. So here we have a smaller arrow of carbon dioxide coming out of the atmosphere into a smaller pool of forest, and then we've got the same amount of energy going back into the energy production system, back into the atmosphere. We end up with more carbon going back into the atmosphere. So an example that would work nationally, that would be relevant to this, would be, say, if we converted old growth forest into bioenergy forest or short rotation forest, we would end up with a situation that we don't want like this. So I thought I'd just put this in here and just put a sort of important caveat here. So what this slide talks to here is the idea of converting existing plantation forests. I'm not talking about short rotation forests, bespoke bioenergy forests here. What I'm talking about here is the idea of converting existing plantation forest systems into bioenergy forests. And there are some risks here that the net emissions outcomes from existing plantation forests can go both up and down, and they rely on careful management. So you can end up with a situation where you convert your plantation forest into a bioenergy forest, it increases the rate of harvest, and your total biomass goes down, you end up with more emissions, net emissions into the atmosphere. Equally, you can actually manage it effectively and increase the stock in that biomass, in that plantation, existing plantation forest, and go the other way and take carbon out of the atmosphere while creating energy. So it requires careful management, and that varies around the world. I'm pleased to say that in New Zealand, forest carbon stock is carefully managed by legislation, and generally it's carefully managed to increase the overall carbon stock of our productive forests, our commercial forests over time, which is okay. So I also had a question about residual or waste forest biomass. So this is the stuff that's left over after harvest. This can also be the waste that's produced through wood processing. So waste or residual forest biomass can be left to decompose back into the atmosphere or to make wood products. So we can leave it on the ground. Essentially, what we're looking at here is a 1 to 10 year return of carbon back to the atmosphere as this waste material decomposes, or you make it into short-lived wood fibre, wood products. And some of those generally will get disposed of, burnt, and they will be returned back into the atmosphere. So maybe some of that material will return back into the atmosphere within 1 to 10 years. So in principle then, the carbon cycling process with this residual biomass is very similar to that of forest bioenergy. So it's not necessarily something that we want to do instead of using this material or woody material for bioenergy. Instead of using residual biomass and leaving it on the ground or turning it to wood products is not necessarily something that is always the best thing to be doing, because we can use it for bioenergy, which will displace those carbon emissions from fossil fuels. Okay, so back on to kind of the research that I've been doing at Scion with our team at Scion. So how effective is short rotation forestry for reducing emissions? This kind of ties in quite nicely with some of those questions, and this is specifically focused on short rotation work. So what we did here was conducted a net life cycle emissions analysis with short rotation forestry, and this was in collaboration with researchers at Motu. It was a life cycle assessment of net emissions from short rotation forestry. We compared the life cycle emissions with other land uses on low producing grazing land. And what we also included in that assessment was the emissions displaced from coal. So why are we doing this, and why are these big questions around this area? Well, obviously you're very familiar with these emissions graphs, the projected emissions graphs of the future, and what we're trying to do is to get onto this amber line or these blue lines down the bottom here. And the idea is that bioenergy should help us be one of the strategies that allows us to get back onto those tracks rather than the tracks up top. And also, there's been a whole range of both scientific and public debate about not about short rotation forestry, but about bioenergy from forests. And a lot of studies, a lot of papers published over the last 10 years or so. Some of them will say it's absolutely totally a bad idea. Some of them will say this is a brilliant idea, and the other guys have got it wrong. There's no consensus in the scientific literature around this. So this was another reason why I wanted to specifically look at our study in New Zealand, looking at short rotation forestry, and work out where does this fit in this big debate. Okay, so this was the analysis that was produced here. So I'll just talk through this graph. It's admittedly, I can understand, a little bit complicated. There's a lot going on here. I'll start from the top. So we have on the top here is net emissions. These are positive emissions over time between 1 and 50 years. And that dark blue line on the top there corresponds with sheep and beef emissions. So from that grazing land, you've got ongoing emissions, equivalent emissions of CO2 from methane, nitrous oxide, and so on and so forth. So that sheep and beef grazing land is a net emitter, ongoing net emitter of greenhouse 14 gases. Moving down through here, we've got an orange line at the bottom here. So this is a net sequestration, negative emissions from carbon forestry. So this is plant and leaf, exotic plantation carbon forestry using Pinus radiata. And does what you'd expect. It's intended that that system takes carbon out of the atmosphere and you gain those carbon credits, economic carbon credits from that. Up at the top, near the top, we've got a lighter blue line there, which is native forestry. So that's the idea, you're planting native tree species and you're leaving them and letting them to take into the carbon from the atmosphere. And you can see that the native species grow a lot slower than the exotic species down the bottom, approximately about 10 times slower than the exotic species there. And in the middle of the graph, we've got these two sawtooth or zigzag lines, and they respond to productive commercial forestry types. So the green one is your conventional 28-year Pinus radiata plantation forestry regime, and the purple one is short rotation forestry. So here we're looking at a short rotation forestry regime for 16 years. 16 years, cut it all down, turn it into bioenergy. The green line is the plantation forestry, as I said, so it gets harvested at 28 years, and I think off the top of my head, I think it's about 60% of that above ground biomass gets harvested, and the rest of it gets left as residual biomass to rot over time. And that curve you can see in that line there is that decay process taking place while the forest is actually being replanted. Okay, so what can we take from this graph? We can say if we wanted to reduce emissions on grazing land, we would stop grazing and we would plant carbon forestry. We'd leave that. Okay, job done, easy. Okay, there's probably a little bit more to it than this, so I'll move on to my next slide. Here I've taken off that sawtooth line from 28-year plantation forestry just to clear things, just make things a bit easier to understand. And what we've got is that sawtooth line that remains from bioenergy forestry. And what I've done here, what our team has done, is build in the net emissions from that commercial system with short rotation forestry, build in the net emissions from harvesting, transport and production of wood pellets from that biomass harvested from the forest. And what that does is change our sort of net neutral system into occasionally a net positive system until the forest grows again and takes more carbon out of the atmosphere. Okay, so not looking good so far, because we can say, again, looking at this, short rotation forestry is looking even less favourable. They definitely would want to transfer from sheep and beef grazing back to carbon forestry. Again, that seems like a bit of a no-brainer so far with this analysis. I also mentioned earlier that I quoted that figure of minus 0.1 kilograms of CO2 equivalent emissions per gigajoule of energy produced by short rotation forestry. I just want to show where that comes from. What we're doing here is assuming an average carbon stock in this forest over time. So averaging that carbon stock, and what you end up with is a negative value of a negative value of emissions per hectare. If you convert that into the amount of energy per hectare, it works out roughly at minus 0.1 kilograms energy CO2 per gigajoule of energy produced. So I just want to show you where that comes from. Okay, so I also mentioned at the start of this that we wanted to build in those displaced emissions from fossil fuel emissions, from fossil fuel burning. So what we're obviously growing that bioenergy from short rotation forestry for is the displaced emissions from coal burning. So this graph here takes that into account. So what it says is it builds in all of those net emissions, lifestyle factors from the transport and production and so on and so forth. But it also says for the amount of energy that you've produced from this hectare of forest, you're now displacing the equivalent emissions from coal burning. And if you build that into that analysis, we end up with a very different presentation here, which tends to show that short rotation forestry actually comes out as a bit of a winner in terms of reducing net emissions overall by building in that emissions factor from coal burning. So I was actually quite surprised to see this result. One of the reasons why I wanted to do this analysis was just to really test the effectiveness of this, and I thought it was going to come out somewhere in the middle here. but it really actually comes out very strong. And in a way, it actually indicates, if you look at the trend on this line here, it looks like short rotation forestry is a more effective net emissions reduction system than even carbon forestry, ongoing carbon forestry. Okay, so time, good. So moving forward, so just to sort of give you a bit of an idea about where we're heading with all this work. So a lot of everything I've done so far has been hypothetical. It's all theoretical. It's desk-based. And one of the things that'd be really valuable in this area is to start up some short rotation forestry trials. So if you actually get those trees in the ground, get a real understanding of how they grow in those high stocking densities, and so on and so forth. So we've been approached by MPI and Environment Canterbury to start start thinking about some experimental trial design. So hopefully those will go ahead in the next few years. We've also conducted a range of short rotation forestry trial plot measurements. So that might seem a bit surprising, because I think I've said this is all hypothetical and we haven't actually got any short rotation forests. But what we've actually managed to do is identify existing areas of the commercial forest estate nationally that have characteristics resembling short rotation forests. So this is Pinus radiata and Eucalyptus fastigata, 4 to 20 years old, individual stands of that. And that is stocking density of 670 to 1400 stems per hectare with unpruned, unthinned trees. And so what we were able to do is go along to each of those stands, measure the trees, see how healthy they are, work out the carbon stock, and so on and so forth from them. And in addition to that, we've also found a number of areas on the existing permanent sample plot networks. I'm not sure how familiar you are with that, but nationally there are a range of permanent sample plots where people have measured parts of the commercial forest estate, and also we've been able to extract those measurements and get an idea of the growth rate and the health of those trees. I mentioned at the start of our talk from our workshop that we really wanted to engage growers and investors. So we've done exactly that. In the last 6 months, we put together a short rotation forestry handbook. So this was summarising our research into accessible language for growers, investors and government agencies. It gives all the information that I've shown in this talk. So it gives recommendations for the species, the regime criteria and the planting locations that this will work well in. And it summarises our information, and the QR code if anyone wants to download that. So we have physical copies or it's available electronically. We've also put together a summary report, which gives a detailed look at our short rotation forestry work. That gives a more detailed impression of the analyses and work we've done, so that's available for download on the QR code there. And then I'd just like to leave you with some final thoughts. So, that green dot on the top left-hand side of the satellite picture there gives you an idea of what 150,000 hectares look like nationally. So that's less than 1% of our land area. A short rotation bioenergy forest of that size, given our assessment and our understanding of its productivity, would be able to deliver bioenergy equivalent to the 5% of our current annual fossil fuel energy demand. So to be able to effectively displace emissions from that demand nationally using that size land area. So 5% of our current annual fossil fuel energy demand is 3 megatons, 3 million tons of CO2 emissions from oil products, or 4 million tons CO2 from coal. So I think we can agree that perhaps a short rotation forest the size of that green circle there is something that's feasible in 10 years or so. We can actually set that up and get that achieved. Okay, so some take-home points to think about. So short rotation forestry can supply an emerging bioenergy market expanding rapidly over the next decade. Forest bioenergy, and this is similar to any other forest harvest product, can have net neutral, negative or positive emissions outcomes, and this depends on the management of the forest system. In New Zealand, all forests are managed to maintain or increase carbon stock over time. So that shouldn't be a risk in our country. Short rotation bioenergy forestry in New Zealand has the potential to increase forest carbon storage while providing an important transition energy source for hard to abate sectors. A shift in land use from marginal sheep and beef grazing to short rotation forest stands reduces net emissions while also producing energy. And we can decarbonise 5 to 6%, something around there, of our current annual fossil fuel emissions using less than 5% of the land area currently used nationally for sheep and beef grazing. Finally, short rotation bioenergy forestry works alongside all other circular bioeconomy actions to reduce net emissions, including all other sources of renewable energy. Thank you.
Sure, Alan. So we've got time for questions. Okay.
Could I ask what the ability of the land is to support aggressive, can I use that word, growth of forests? High density, rapid turnover. I'm just feeling for the land. I'm exhausted already.
Yeah, some good. Yeah, it's a good question. So, in terms of its productive capacity, that land is just sort of talk about the mechanics of it really. So that land is already enriched with fertilizer addition from grazing. So it's already got a
begin with.
To begin with, already there.
Yeah.
So that the productive capacity of that land is built in. There'll be a legacy of fertilizer built into that soil that will last for at least a few rotations. The forests themselves, arguably, you can say that planting trees on land that is pasture will reduce the erodibility of that land. It will increase the capacity of that land to absorb and retain water and not have overland flow, flash flow of water and so on and so forth. The only, I'd be pragmatic about this and say that I acknowledge that there are potentially some risks with harvesting, uprooting machinery on some of those lands, as opposed to grazing, where you're just having sheep and cattle running over that land. So I wouldn't necessarily say it's all bad. I acknowledge that there are some potential risks in how to make this work, but in some respects, it's a lot better than sheep and beef grazing. Does that answer your question?
What was in my head was really a question of chemistry, not that I'm a chemist. That amount of aggressive growth on a paddock of land, I would think would generate a net reduction in the growing potential of that land, sustainably.
I think it might do over a number of rotations. I think immediately it wouldn't. Yeah.
Okay, we've got a bunch of questions online, many from Chris, so we're going to alternate between Chris's questions. So the first question Chris has is, Genesis is looking for biofuels to replace 300,000 tonnes of coal. Is that feasible? And so in what time frame?
300,000 tonnes of coal. Yes, it is definitely feasible. Yeah. In which time frame? I would have to go back and look. But I mean, the shortest regime we looked at was 12 years there. So. Yeah.
So just a point of clarification there. You had the stat of short rotation forestry over 150,000 hectares can provide 5% of our is it energy?
Yeah.
Is that 5? It can do that once every 16 years or every cycle, or
that is ongoing. Yeah.
So we've got a question from Michael Thompson. How attractive is short rotation bioenergy compared to other forestry land use on hilly marginal land use classes?
Yes.
Would the sites be more attractive for higher value plantations?
I think the answer to that is probably it depends. It depends on a lot of things. So I think in terms of conventional plantation, harvest, forestry, the value of a lot of the timber under current market conditions is dropping, and I think they're looking at selling high value timber at a pulpwood price in certain areas. So I think that's a bit of a challenge, actually selling the products at the moment. So in that respect, it wouldn't be competing. I think the only potential competition might come from carbon forestry. So it depends on how high the carbon price goes up, but it might be more economically attractive to plant and leave and just take in those carbon credits.
Do you have a question?
Accepting there's a negative perception about monoculture of plants, and that's obviously a cost we carry as a country. Is there any real opportunity around designating a small proportion of level 3 land can be developed? So we don't have to, you can have a level 2 grazing land with 10% of it level 5. And can we be more selective and turn it into a garden in the country rather than, because there's going to be more than one product from any one activity to really make it profitable. And if you look at the farming sector, if you have an animal that just produces meat, it's not profitable. But if it produces meat and something else, it's valuable. So I'm just asking the question from a point of totally.
Yeah, no, I totally agree with that point. And I mean, it's another piece of work we did at Scion, which was looking at some mosaic landscapes, mosaic forest landscapes and different land use. And I think there's a lot of value in doing that rather than creating these kind of siloed landscapes. Again, I think a lot of it comes down to economics. If you start moving on to the lower land use, the LUC classes, you run up against the high value of that land, which is not necessarily a problem depending on how much you want that bioenergy. So I am aware of some high users of coal who are very much interested in planting up lower LUC classes of land, potentially planting up those lower NU classes of land with some form of biomass. That could be coppice, that could be anything, because they're just going to need that and they're going to need it on their doorstep. And it doesn't matter whether that is high cost land, they're just going to grow it and use it. So,
well, if you look historically at New Zealand farming, they always planted a little bit of forestry for the daughter's wedding or for retirement. This was a completely different type than a farm.
So another question from online. Can you describe the costs associated with gathering waste or residual forest biomass versus the costs associated with short rotation forest harvest?
I think I would struggle to answer that question definitively. I think the answer is no, I can't, because that's not my area of research. But I do have colleagues who are working on that. And so we have other people in our team that are working specifically on residual forest biomass. It must be economic to harvest that residual biomass. I'm sure there are technical challenges to it, but it must be economical to do it. Otherwise, they wouldn't be looking at it at Scion. As to where we stand in terms of the differences in costs, I don't.
Can't be expected to answer everything. Florence, Reynolds has asked, can you please expand on forest management to increase carbon stock held? Could the age of trees that harvest be increased, or are there other techniques?
So I think that relates to the idea of existing plantation forests and how if you harvest them, how do you increase the carbon stock of those forests, whether you're harvesting them for bioenergy or whatever you want to harvest them for. But we'll say it's bioenergy for purposes of this talk and this concept, this question. So yeah, I think the answer is kind of actually in the question there, that you can increase the carbon stock of those commercial forests either by increasing the area, the actual extent of those forests themselves, or by increasing the age of the forest. So if you reduce your rotation frequency or you increase your rotation length, you will have an impact of increasing the standing carbon stock of that forest, which will take more carbon out of the atmosphere. that is probably not attractive to commercial forest organisations, investors in New Zealand currently. But yeah, that would have a big impact on beneficial impact on net carbon emissions. If I just talk a little bit more on that, some of the arguments against forest bioenergy that I've read in the scientific literature have taken a view that in order to use bioenergy from forests, what you're going to end up doing is reducing the harvest rotation length of those forests. And the studies that I'm referring to here, I think we're looking at European forests, and they're taking some hypothetical scenario whereby bioenergy demand in Europe becomes very, very high. The rotation lengths of those forests are reduced, and what you end up with is a carbon debt in terms of the actual standing stock of carbon in those forests as a result of the reduced rotation lengths. And that was a source of a lot of the debate, saying, well, this is ridiculous because it's going to take you 400 years to build up the difference in carbon emissions from the standing stock of that forest. But that's not what we're talking about here.
Sure.
How does fire risk play into these equations?
I guess in the same way that it builds into anything with forestry in New Zealand, in that it is an existing challenge that can affect any forest. In terms of short rotation forests, I guess you could argue they are potentially more fire risk because you've got lots and lots of standing biomass. You've got potentially smaller trees that are more combustible. So yeah, it's one of the risks that we would have to look at. Yeah, certainly.
Yeah, that's right.
Yeah, that's that -0.1 kilogram. So what I understand is that the negative is because you're taking credit for the land use change going from farmland to forest. Is that right?
Yep.
So, but that would be kind of like a one-off benefit. Over. So I guess over like a longer time frame, so we could probably take credit for that over, I guess allocate that over a certain number of years, and then at some point that kind of, I guess, gets kind of written off over a certain number of years. So I suppose in the long term it will go back to maybe closer to zero or slightly.
Yeah, certainly. So I mean, yeah, it's a little bit perhaps oversimplifying things just to kind of make a point there, and I acknowledge that there's a lot of variability and a lot of transition that would take place in that over time. So that negative 0.1 of a kilogram CO2 emissions per gigajoule equivalent apply to the first rotation, and over time, yeah, you get that would get less and less over time, producing more energy. I guess I might have to go back to my slide just to kind of talk through that. Actually, is that possible?
But not with my.
Not with that. No, don't do that. No. So yeah. Oh no, I'm on that. Okay. I'll just try and talk through it. So yeah, I mean, I accept I'm kind of oversimplifying that, but just to kind of make a point that there is potential to have negative emissions and produce energy for the first rotation, and it's worth bearing in mind that there's other sources of renewable energy. While short rotation forestry is negative, they're actually all positive, just slightly, but they are positive. So there is a bit of a difference.
Sorry, I've lost it completely.
Okay.
So we'll have one more question, and then we'll wrap it up, I think. So the last question here is around East Coast, and is that a good idea given the erosion risks?
Yep. Yeah, that's a very, very good point, and something that we definitely recognise in our work. The East Coast has advantages in terms of it has lots of cheap land. It's brilliant growing conditions for forests. But yes, there are erosion risks, there are slash risks associated with this. So I guess what we're saying is, just like any forest, with short rotation forestry, you're going to need to plant it. You're going to need to make some very, very careful decisions about where you put it and whether that's appropriate to put it there. I think in the East Coast, there will be areas where it's appropriate to plant short rotation forestry. There are obviously areas where there are erosion risks and slash risks that you wouldn't want to do that. So we're not saying blanket East Coast is all going to be good, but there are going to be, you have to make some very careful decision making there. So acknowledge the erosion risks in the East Coast, but also say there is a potential opportunity, particularly with decentralized processing, also that alluded to there. One of the things I would say in short rotation forestry's favor is that with that harvest for biomass, what we'd be looking to do is cut the trees down, but then absolutely remove all that's on the ground, every limb, branch, everything. So there would be no slash left remaining for overland transport into rivers and so on and so forth. So yeah, just put it where it's sensible. But the East Coast, some areas in the East Coast, I think would be good.
Great. So that was a very controversial topic, and thank you very much for trying to address all those questions and coming here and and speaking to them. That's fantastic. So we'll thank thanks everyone online. We'll see you next time.